Episode 176 of CppCast with guest Jeff Amstutz, recorded November 21st, 2018. Today's sponsor of CppCast is the PVS Studio team. PVS Studio can be considered both as a tool for finding errors and typos and a static application security testing tool. The tool supports the analysis of C, C++, and C# code. And by JetBrains, maker of intelligent development tools to simplify your challenging tasks and automate the routine ones. JetBrains is offering a 25% discount for an individual license on the C++ tool of your choice, CLion, ReSharper C++, or AppCode. Use the coupon code JetBrains for CppCast during checkout at jetbrains.com. In this episode, we discuss cute WebAssembly apps. Then we talk to Jeff Amstutz from Intel. Jeff talks to us about SIMD and SIMD wrapper libraries. Welcome to episode 176 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today? Happy Turkey Day.
Happy Turkey Day. It's Wednesday, technically.
Yeah, tomorrow's Thanksgiving, though.
Well, yeah, yes, and happy Thanksgiving. Sorry, I guess I'm a little distracted and tired and such.
It's okay. Okay.
But I was just thinking this time as you read the first podcast, because we've read this many times, right? Mm-hmm. The posts that you make to the ISO CPP website still say the only podcast for C++ developers.
Right. I need to update that. I always just copy paste it from the previous post. Yep.
I think it's fine if you leave it.
Well, Phil actually pointed out to me that the tag and the metadata for the website still said the only podcast.
Oh, is that right?
To me so I could update it recently. Yeah.
Yeah, we'll just keep it subversively like that for a while. Don't tell anyone. Shh.
Okay. You have anything fun planned for Thanksgiving?
Thanksgiving, hanging out with family. It'd be a pretty simple Thanksgiving.
Okay. Yeah, we're doing a Friendsgiving down here.
With the level of travel that I've been doing lately, our plan is basically to not travel on holidays.
That's a good plan. I'm not a big fan of Thanksgiving travel either. Yeah.
Yeah.
Okay. Well, at the top of every episode, I'd like to read a piece of feedback. This might be our first YouTube comment. And this is from John on the episode from 2 weeks ago with Devin Labrie. And he wrote, I'm not sure if this is the best place to post a comment for the podcast, but I'm really impressed with CppCast. I like how you guys mix things up, having folks from various levels of C++ skills in the show. I've had an itch multiple times to delve into the game arena, but have been redirected by career choices. I really feel for Devon and hope him well on his game dev adventure. He also says that outside the other awesome game-related guests in past episodes of CppCast, I would suggest Devon have a listen to the Game Dev Unchained podcast to get a good feel of the game industry, in particular the episode with John Podolisic. This was an eye-opener for me, so it may be of interest to him as well. Thanks, Rob and Jason, for posting these great podcasts, and I look forward to the future episodes. So yeah, I'm glad to see we got some nice YouTube comments. Usually YouTube comments are a bit of a cesspool, but we're getting good ones.
And I guess for our listeners who don't know this, you do post the episodes to YouTube every week, right?
Yeah, I think we just started doing that this year, but I've got 3 years worth of the show up there on YouTube now.
And a kind of a side benefit of that is YouTube's automatic transcription service is going to come into play. So there are transcriptions of the episodes there. I'm sure not perfect, but they do exist.
Yeah, they are there. Okay. Well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us reviews on iTunes. Joining us today is Jeff Amstutz. Jeff is a software engineer at Intel, where he leads the open source Osprey project. He enjoys all things ray tracing, high performance and heterogeneous computing, and code carefully written for human consumption. Prior to joining Intel, Jeff was an HPC software engineer at Service Engineering, where he worked on interactive simulation applications for the U.S. Army Research Lab, implemented using high-performance C++ and CUDA. Jeff, welcome back to the show.
Hey, thanks for having me.
Hey, Jeff, I mean, this is your second time on the show, and it's been a long time, and we'll talk about that more later. And I can't remember if I asked this before, but you say you enjoy all things ray tracing. How did you get started with ray tracing? That's like the oldest ray tracer you played with.
Well, I got started in ray tracing because of my first job at Service Engineering, doing ballistic simulation.
Okay.
So I didn't really play with a lot of ray tracing packages. I played with the one that Service made. It's called Rayforce. It's actually open source up on SourceForge. And that one was good. But Service Engineering was about making products to solve problems for customers. So eventually, the Embry ray tracing kernels that we have at Intel kind of eclipsed the need for Rayforce to exist, at least when I was at Service, and I believe they continue to use our Embry ray tracing kernels. So now the ones that I was playing with at Service are now the ones that I help maintain at Intel.
Okay.
Yeah.
Awesome.
And that was starting back in 2012. So, yeah.
2012. So do you have any experience with like the old like PovRay, MoRay, like some of those old open source ones that started that world?
No, I definitely need to go back and educate myself on the history of ray tracing before my time. That'd be a fun time.
Yeah, it could be fun.
Yeah.
Okay, Jeff, well, we have a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about maybe ray tracing and more about SIMD, okay?
Sounds great.
Okay, so this first one is a trip report focused on the freestanding proposal, which Ben Craig is working on. We talked about freestanding with him earlier this year, and he was at the San Diego meeting presenting updates to the freestanding proposal, I guess, and he's giving a rundown on how that went. It seemed like it was kind of a mix of both good and bad. He seems like they're getting a lot of direction. And he kind of pointed out that he kind of did his whole proposal kind of backwards, where he made all these suggested changes first and then is just now getting direction on what the committee, will go for.
Yeah, it does seem like the backwards way to do it.
Yeah, which he pointed out.
It does feel like good news that it is moving forward, it seems.
Yes. Yeah, and it seems like he is kind of getting some recognition at around the committee meetings. Like everyone recognizes him as the freestanding guy now, I guess.
That's cool.
Nice. Yeah. Is there anything else you want to point out in this, Jason?
No, but I was just in my head thinking the freestanding guy. He's the one over there by himself without anyone. I mean, it's freestanding. It does anyhow. Sorry, that's bad.
Next, we have a post on the Qt blog, and this is getting started with Qt for WebAssembly. And this is pretty cool. This is a post just going through what you want to do if you want to make a kind of a hello world type application using Qt GUI controls in WebAssembly, which is pretty awesome that you can do that. And they also have a link at the bottom to a sample application, which you can go and check out, which is like this little image editor, but it's running in WebAssembly, which is pretty cool.
That's just amazing to me. Have you messed with this at all, Jeff? WebAssembly?
So back in my DoD contracting days, I had lots of experience with Qt. Like that'd be the late 4.8 and early 5 stuff. And so I haven't played with Inscriptum at all, but when I go down on this article and I just look at the screenshot of this little Slate application that they made with this, I went, oh my gosh, that's really cute in a web browser. That's impressive.
Yeah, your brain kind of gets confused because you're like, okay, there's a URL bar at the top, and then wait a minute, there's like the whole application running right there. Yeah.
It's crazy.
So that's really impressive. I think that's some great work, and maybe one day I'll play with it.
Yeah, I need to play with it as well. Some of the projects I'm working on right now would be well suited to playing with it at the very least.
Yeah. Well, one thing I want to highlight for our listeners in this post is that if you're interested in this, they're going to be hosting a Qt for WebAssembly webinar on November 27th. So that's sometime next week. I'm assuming that's free to join and learn more about it. Yeah.
It does appear to be free.
Yeah.
Yeah.
Does it say how long the class is going to be? The webinar?
It says it starts at 2. Oh, it starts at 2 and ends at 3. Yeah.
Okay.
Although it doesn't say what time zone it's in unless it's automatically adjusted to the current time zone of the viewer.
That would make sense. So last thing we have is Herb Sutter's trip report from the San Diego meeting. And obviously we talked a bit about this last week with Ashley, and I think we're going to still have a second part 2 trip report with another guest hopefully next week. But is there anything you wanted to highlight from Herb's trip report, Jason?
Yes, there was one thing that caught my eye that I did not hear anything about before this. Looking through the trip papers and everything else, I had not seen anyone else mention bind front, which Herb mentions here. Bind front, it's like one of the last things. It's like bind first from back in the day from C++ 98 was terrible. It only worked with like a 2-parameter function or something like that and returned a new callable thing. And stood bind is just in general terrible because it's way overcomplicated, adds considerably to compile times, and if you're not lucky, it also adds runtime overhead. Depends on how much the compiler can see. But it looks like this bind first is just bind the first argument and return a new function that takes the remaining set of arguments. And I've written this a couple times myself with variadic lambdas, and it's a fairly straightforward thing in the simple cases to do. But definitely a handy thing to have when you need to be like passing functions around and you're like, oh, well, I just want to partially bind like just the first function, pass it on to the next thing that doesn't care about it, bind the next thing onto it or whatever. It definitely has uses. It's just cool to me to see something that's kind of in between this crazy world of stood bind and the old outdated world of bind first. So
would that make it straightforward to implement like a bind n, like bind first 3?
Yes, but binding only the third element is still quite
that's
annoying.
Going to be tricky. Yeah.
Yes.
This would be up to n, not the nth one.
Right. Yeah, you could totally do that. You could easily just write a function that takes 3 arguments and calls bind first 3 times. Now, granted, you're going to making the compiler work a lot because it's going to generate effectively a variadic lambda for each of these things and then have to optimize them all, but it can.
Yep.
So...
Okay. Cool. How about you, Jeff? Is there anything you wanted to call out from this trip report?
There's all kinds of stuff. The fact that ranges and concepts are in C++ 20 is just huge. It's really, I heard an anecdote. I was at the supercomputing conference last week, and I think I overheard someone talk about like when ranges got voted in, there was just this standing ovation in the room. That's because it's a huge body of work and such a big change for C++. So that's really cool. And then the one thing I'm looking forward to, based on this trip report, is the is constant evaluated. That sounds like it's going to be really useful to kind of be able to constrain, like if someone accidentally uses some kind of constexpr feature in your library or your code, and it ends up becoming runtime, and you want to explicitly say, don't do that. Now, here's a trait that you can use to explicitly maybe use static assert to enforce that.
Yeah. It's, It definitely opens up a lot of doors for craziness.
Yep.
One more thing.
You just said,
go ahead.
No, go ahead, Rob. Sorry.
I was just going to say one more thing. I'm not sure if we mentioned this earlier, was they're creating 2 new study groups, machine learning and education, SG19 and SG20. And the education one sounds interesting. It has the aim of trying to improve the quality of C++ education in universities. And I think we've, talked to various guests on the show about how that's very hit or miss, how well they teach C++ at universities these days. So
yeah, well, Reddit.
Yeah.
Sometimes you'll read a comment on some C++ related thing and someone will be like, oh, well, my professor told us to do this. And then you basically get responses from other Redditors that are like, you need to go to a new university, basically. But I am curious, Jeff, you just said you were at the supercomputing conference. What kind of a representation does C++ have there?
it's a mix because, you get some old school Fortran C, codes that have been around forever. And then, there's definitely a plenty of demographic of C++ programmers looking to do very state-of-the-art C++ kinds of things. There's a number of libraries out there that are focused on kind of HPC distributed computing. There's HPX, Raja, Legion, and there's some others. And those folks are always trying to push C++ forward to do things like heterogeneous computing. How do I write a program that will get distributed on a cluster without having to manage all the networking stuff? There's really cool stuff going on. And then on top of that, there were even a number of C++ standard committee members that showed up at SC exhausted from San Diego.
Wow.
And, there was a Birds of a Feather session on C++ for heterogeneous computing. So in HPC, being able to have a number of GPU accelerators or FPGAs alongside your CPUs, how do you program all those? That's definitely a problem. Bigger than HPC, but the HPC folks are also interested in those.
Cool. And if I heard this right, is this the conference that's going to be rotating back to Denver next year?
Yeah, so if I play my cards right, if I go to C++ Now, I'll be in Denver for CPP Now, CppCon, and SC.
All right.
So
stop by and visit my meetup.
Yeah. If I'm in town, I'll definitely look for it.
Okay, well, as we said earlier, Jeff, you were on the show once before, but it was back in March 2016, about 2.5 years ago. So what's happened since then in your life?
So the Osprey project, I've kind of stepped into a role of leading that. There's a number of engineers at Intel that all contribute to it, and we're all kind of one team, and that it's been great to work with them. Mostly based out of Austin. We also have some folks that work out of Germany, and the project's it's been maturing over time, which has been great. User base is just growing and growing. It's been a really fun project to work on, and now I've kind of also added onto my plate there are future undisclosed hardware coming from Intel, as you would always expect. And so one of the things that you have to do with that is make sure that it's programmable. And so stepping into how do I talk to the right compiler folks at Intel to make sure that things like Osprey are going to properly map to whatever hardware comes out. And so that's been really fun as well, because Intel has definitely, made plenty of its money and profit and user base buy-in with its CPU, like OpenMP Pragma-based SIMD programming, and we'll talk about that maybe a little later. But kind of branching out into other things is really fun, and we'll see what happens in the coming months.
It seems pretty crazy to be able to get to kind of live in this world of experimental hardware with compilers, and will it work with the tools that you're working on? Yeah,
it's simultaneously exciting and terrifying, because it's one thing to play with it. It's another thing to say, well, I also have to ship this library that's going to be live or die by how well these tool chains work. So we'll see.
It also seems like your program crashes, and now you're saying, is this a bug in my program, a bug in the compiler, or a bug in the hardware? Yeah. Which most people don't have to stop and ask usually. Yeah.
My best experiences have always been when the hardware is not buggy anymore. I try to not get involved with hardware that's so early revision that it's going to have known problems. So by the time it gets to me, it's a matter of programming it right versus making sure the thing's actually working. That's crazy cool. Stories about that stuff, but that's for another time.
Yeah, probably some you can't talk about as well, I would imagine.
Yeah.
So you just presented at CppCon compute more in less time using C++ SIMD wrapper libraries. You want to tell us more about your talk?
Yeah. There's multiple ways you can get a compiler to generate SIMD instructions, and I'll just back up and explain what that is, and then what the talk is covering. So SIMD stands for Single Instruction Multiple Data, And what that is if you think of like a normal mathematical expression, like a plus b minus c, and we'll assign that to d. So it's an add and a subtract. Normally that's going to operate, each operator is going to operate on one value on each side of that operator. So if those are all floats, it'll do, add two floats together and then take that result and then subtract two floats, and store that in a float or whatever. And so SIMD says, okay, that each one of those operands, like the plus and the minus, those are each basically an instruction. So what if we could have one instruction that instead operates on multiple data values at the same time? So if I have an addition and then followed by subtraction, but I can apply those on more than one value at once, then I can actually increase the amount of computation I've done in the same number of instructions. So it's called vectorization. Instead of having a single value, which we call scalar values, you instead widen those to a vector width of something your hardware supports. And then that lets you just do this more computation at one time, which hopefully speeds up something that needs lots of computation done. So with that concept, there's a number of ways you can make a compiler generate these special instructions that exist on all kinds of different CPUs, and it turns out GPUs are pretty similar. Obviously, there's going to be lots of devil in the details that are very vastly different, but at kind of like a high level, they're looking for the same thing. I want a single stream of instructions that's going to map to, collections of values instead of single values. And so there's multiple ways you can get these instructions generated by your compiler. There's some trade-offs with different ones, but when you want to look at idiomatic C++, like I want to use the type system to do work for me, I think the best way to do this is with what we call a SIMD wrapper, which is I represent these. So if I take a built-in float and I want to instead create a type that represents 4 or 8 floats at a time, we can use the type system in C++ to create that type for me. So then I can say, a plus b minus c, those each can be represented as a float 8 instead of just a float. But everything else then is the same. The plus looks the same, the minus looks the same, the assignment. So the idea is things that are normally kind of complicated to get these instructions to like deterministically come out of the compiler, these type of SIMD wrapper libraries make that look like your normal code. And so the talk was not trying to sell anyone on a particular library, because there's a number of them out there. There's actually one now voted into the standard. So that's all great. But rather the talk was, hey, here's the kinds of problems we're solving. Here's the common things that are going to be in all of these libraries. So when you go play with one, these are the things to look for. And I hope that's like a nice foundation that then maybe next year there can be some more advanced, like, all right, how do we take, scalar existing code that isn't vectorized, and, now what are some techniques that we can use these libraries to then write vectorized code?
I want to take a quick aside to data sizes, since you're talking about these things being packed into things that the CPU can support. Mm-hmm. And you say float, and I know floats tend to be used a lot because they're small. You can pack many of them, and like a double, you can have fewer. Long double, maybe only 2 or something in a SIMD instruction. If the CPU even supports long doubles, I don't even know. Where's the trade-offs on these kind of decisions?
So a couple of things there. One is most SIMD instruction, or pretty much all SIMD instruction sets, they measure their register sizes in bits and not in number of elements of a particular type. Okay. So like for machine learning, there's a lot of cases where precision is not as important. So you can get more speed up by cramming more lower precision floats into a register of, like, let's say AVX and AVX2, most modern Core I series CPUs out of Intel, will have 256-bit registers. So, if I can cram 8 32-bit floats into that, that's great. But if I don't need the precision, I can make that smaller and use maybe half precision. Or the other way around, which is the world that I usually trade off with, the 32-bit float being the less precise for doubles.
Right.
Where scientific computing, all that precision is desirable. And so, it's pretty much precision and what you're doing. And then, of course, for integers, the same thing is true. If I only need to represent 255 values in my computation, then I can cram a bunch of 8-bit integers into a register versus, using full 32-bit ints or 64-bit ints.
So are these AVX or whatever on the appropriate platform instructions flexible enough to say, I've got a pack of 8-bit floats, if you had some way of representing that?
Yeah, the way, to not get too into I don't want to lose any listeners with getting too into the weeds.
That's fine. They tell us to get more technical anyhow.
Yeah. So I can represent, here's a collection of ints, but most instructions will then have, here is the expected collection of elements you're going to use. So, I can't remember the intrinsic names. So intrinsics, for listeners that don't know, are little C-style functions that more or less correspond to an exact instruction. And so they usually are the implementation detail of what an implementer of a SIMD wrapper library uses to, when I say float 8 plus float 8, I'm going to call a particular intrinsic.
Okay.
So the intrinsics, then they say, here's a 256-bit register of 32-bit floats, and it's an add. And so there's this kind of naming convention to organize all that. So you actually represent the register with the same type. It'd still be an M256 or an M256I. And then it's the particular instructions you choose to get what the element-wise types are going to be, which of course is maddeningly easy to get wrong. So that's why these wrapper libraries are nice, because now we use the type system to enforce some things, to do proper conversions and stuff like that.
So the answer is yes, the hardware is very flexible, but it's not arbitrary. It does have fixed 8, 16, 32, 64, whatever.
Yeah, and usually as instruction sets have moved on through time. So, the difference between AVX and AVX2 is that there was instructions added for additional wider vectors for ints. For AVX1, it was just floats.
Okay.
This is super oversimplified, but take it for what it is. That, it was okay, we'll go from 128-bit to 256-bit, but AVX1 was we're going to do it with floats for the 256-bit operations. And then AVX2 is we're going to add the int support as well. And then AVX 512 that goes to 512 bits added also lots of instructions all over across the board for the 512-bit wide stuff. You can get lost in understanding what the exact instructions that are supported in the instruction set per generation of ISA, then how that maps to your CPU generation, what your CPU supports at runtime, and it's a fun problem to solve that other people then don't have to think about.
Right.
I'd like to interrupt the discussion for just a moment to bring you a word from our sponsors. Authors of the PVS Studio Analyzer suggest downloading and trying the demo version of the product. Link to the distribution package is in the description of this podcast episode. You might not even be aware of the large number of errors and potential vulnerabilities that the PVS Studio Analyzer is able to detect. A good example is the detection of errors that are classed as CWE14 according to the Common Weakness Enumeration. Compiler removal of code to clear buffers. PVS Studio creators demonstrated the detection of such an error type, for example, in one of the latest articles, We Check the Android Source Code by PVS Studio, or Nothing is Perfect. Link to this article is also in the description of this episode. PVS Studio works in Windows, Linux, and macOS environments. The tool supports the analysis of C, C++, and C# code, and Java support is coming soon. Try it today. Okay. Do you want to tell us a little bit more about SIMD and maybe how you use it in your day job?
Yeah. So I'll say this. If anyone who's listening watched my talk, I had a little example, and I got called out for it on the comments because I was dumb and I read the comments for the talk. And
no, you're not supposed to do that.
Yeah. And so I had my first example is called Saxby, which stands for A times X plus y. It's just this like, here's a little formula you can apply to every element in like 2 arrays and store them in a third array. Is your like hello world of vector computing.
Right.
And I said in the talk, like, Saxby's nonsense. And the comment was, this is like the basis for a ton of machine learning algorithms. And what I meant when I was thinking it in my head was, this particular thing I wrote is nonsense. Like, I'm not computing anything. I'm just like taking garbage data in, garbage data out, storing it just to exercise the machine.
Right.
And so, yes, there are plenty of algorithms out there that are trivial to parallelize in this way, which is, for what it's worth, orthogonal to threading. So vector parallelism is like what every thread would be executing. So we're talking about just one of the many types of parallelism you have to go and consider when you're optimizing code. But for me, it's basically any time I have an operation that I'm going to do a lot of the same thing to just a bunch of elements, that's a great candidate for using SIMD. Now, Osprey doesn't use C++ SIMD wrappers. It may in the future. What it uses is actually a small custom language called ISPC, the Intel SIMD compiler. It's a free open source thing up on GitHub, and it's neat, has some trade-offs, and there's tons of details we could talk about why it's different than SIMD wrappers. But anyway, so if you think of ray tracing, the simple way to describe it would be, if I'm trying to model light in some virtual scene, so like I define some geometric objects, some spheres, some cubes, or like triangle meshes, what I can do to get a picture out of that is define a virtual camera and define an image plane, which is basically going to be the screen. And I can basically trace light backwards. You trace a ray from the camera out into the scene, and when you find a hit point, you then figure out what material you hit and what angle you hit it at, and then you can figure out, okay, well, what's the next bounce that the light would have traveled to get to that point, and you keep going until you get to light sources. And that's the basic rendering algorithm. So there's a number of ways you can vectorize these kinds of things. But the way we do it is we take what we call packets of rays. So we'll take 8 rays, out of the screen at a time, and we will trace all of those rays through acceleration structures. When we, want to create like a bounce set of rays, we can do all of that, because we're like, for instance, if I'm creating a secondary ray from like one hit point, I'm going to do the same calculation for all of those rays that hit. So that's a great candidate for SIMD. And where these kinds of SIMD wrappers play in is the way you model that. Like if I'm going to do a 4 or 8 or 16 rays at a time, or even like giant buffers of ray streams, I don't really necessarily have to care about the exact width I'm working with. Of course, when you tune, if I was tuning for SSE or tuning for AVX, maybe I would want to get specific and use like float 4s or float 8s. Mm-hmm. But really, at the majority of the time, I just want to say like a V float, like a vector float, or what I call a varying float. That I just want it to be something that can be widened. And by the time I get to compiling for a particular SIMD register width, I want it to just pick the right thing. So if I'm compiling this for SSE, that V float turns into a V float 4. Or if I'm compiling for AVX 512, that turns into a V float 16.
Okay. So you're saying, just to be clear, 4 floats in a pack, 16 floats in a pack. Okay.
Yep.
I was at first thinking you were saying 4-bit wide floats, and I'm like, I don't even, what could you possibly represent with that? Okay.
Man, that's a really long mantis and exponent and all. That'd be the most useful floating point ever. Anyway, definitely number of floats in a register. 32-bit floats is what I use. We use most commonly. And so I'd say the thing there is, it's always easy to, when you're looking at something like Saxby and you're doing machine learning or something, it's like, oh, why can't the compiler just do this all the time? And it's like, if your math is as simple as that, and you're just doing that very simple expression to a bunch of pieces of data, that's great. You might not need fancy SIMD wrappers for that. But where rendering, ray trace-based rendering is the opposite. What we have is these very deep function calls where, I take a packet of rays and I have to generate the rays from the camera, then shoot them out. I got to traverse them down a bounding volume hierarchy and do ray primitive intersections to get like the normals, the hit point distance. Then I have my material, and I've got to go and figure out, based on that material, how am I going to calculate the next ray that bounces. And it gets to the point where you get two things, very deep, as in several function calls deep on the stack, where it's not all just in this one for loop. I can actually reason about a packet of rays anywhere in the function call stack, because I know this is like a packet of 4 rays. This is a packet of 8 rays. And then the second half of that is with that packet of rays, I can have all these user-defined structures all over the place. And that's where it gets really interesting. Because if I define like an algebraic vector, like a vec3, so like we're representing a point in space, or maybe it represents a direction. Right. So you could define an array as a point and a direction. So each one of those x, y, z points are going to be scale, like in the naive sense, scalar, just float x, float y, float z. But if I want to have like a group of origins, then I could say, well, it's actually x is a float 8, y is a float 8, and z is a float 8. And I can compose this all the way up. So if I have a float 8, I can then create like a point 8. And with the point 8, I can create array 8, and maybe, bigger structures like screen sample 8. And you walk this all the way up where I can say, if I have a varying ray, I now can say that could be widened to be array 4, array 8, array 16, depending on my architecture. And when I say like ray intersect, triangle or something, I can actually implement that in such a way that like all the dot products with that algebraic vector just don't care about the width. You can basically express an entire library in such a way that I can write all of this math the exact same way I would as if I was just playing with plain floats. But now I have a very tight understanding of how it's going to be widened. And this is called a structure of arrays, where, interject anytime if you got questions or anything, but because I can just ramble forever, but yeah. But,
okay. Well, actually, I will pause you for just a moment here, because I'm trying to make sure I'm wrapping my mind around this, and I still keep thinking when you say float 8, I still keep thinking want to think an 8-bit wide float. No, you mean 8 floats wide. Fine. Yep. Okay. So when we, because I'm thinking, int 8, int 8, built in the types from C++ 11. Yeah. All right. So you have your so what I'm thinking is this sounds a lot like data-oriented design.
Mm-hmm. It definitely overlaps with that.
But that tends to be geared more towards like fitting your structs into cache lines and that kind of thing. And you, on the other hand, are doing data-oriented design, if you will, but with a goal of fitting it within the vectorization of the hardware capabilities.
Yep. So it's like data-oriented design for an ISA, not for a memory hierarchy.
Right. Okay. How do those two things interact with each other then?
Well, so that's where you can get endlessly lost in like, design trade-offs that are very, very specific contexts of the code you're implementing.
Uh-huh.
So it's tricky to say like, here's the one prescription for this problem you'll have everywhere and just do this. It's always in context of what you're doing. So for instance, if I take and measure code that is running on a single core, so if I have, if I'm optimizing for, better vector instruction utilization, I can be like reasoning about that code, but if I'm running it single threaded, if I'm looking at my cache probably is going to be mostly stocked full of stuff that core is going to be working on. Mm-hmm. And then as soon as you multi-thread it, now my cache is going to be, thrashed in and out with things that maybe separate threads are working on. And so there's all these contexts of like, when I'm optimizing, you have to understand what state the system is going to be in. It's not just, well, what's just this code doing? It's what's this code doing in context of what the whole machine's doing.
Right.
So that's why it's tricky to say, like, for cache line, like filling cache lines, that's not an issue. But if you're looking to say, could I keep an entire function in cache, like of the data that it's working on, that might be trickier, because that's then the issue. Obviously, cache lines themselves won't be divided by threads, but the greater context of what you're optimizing might. So you might want to arrange threads in a way that they're all trying to work on smaller pieces together instead of spreading them out in your data set and having them working on vastly different pieces. But then now all of that is then going to influence how you're looking at your vector code utilization. Like sometimes, for various reasons, it might, in ray tracing, might make sense to represent your problem with shorter vectors than what you natively can have. So for instance, I talked about that issue where I have rays that come out of the screen and they all hit an object. Well, what happens if some of them hit one object and some of them hit another? Let's say I have eight rays and 4 of them hit one object and 4 of them hit another object. Well, it might make sense that as we do the calculation then to create the secondary rays for each of those, where they'll have to load different data because they might have hit different materials or something. They definitely hit different primitives. It might make sense to rearrange them into 2 packets of 4 and then move on from there. And instead of keeping them all as 1 packet of 8, because they're what we call diverging. They're going different places and they're not going to be doing the same things, kind of by design of the algorithm. So then there's other design trade-offs where you can say, well, I might change that I have a single scalar ray, and then I march that down, and I can do batches of primitive intersections at one time. So instead of doing many rays to one primitive, like one sphere, maybe I'll do one ray and have several spheres that are candidates, and then test them all at once. So all of these things require ways to express user-defined structures that I can say, I want to load a group of spheres that I'm going to call a varying sphere 8, and then test that against array or vice versa. And it gets tricky to do. If you want to do that with Intrinsics, there's 2 problems. One is you end up only implementing it for one instruction set. And it's really complicated to look at. It's almost as bad as assembly. So there's that. And then the other half is things like OpenMP that were more built for Fortran and just pure C don't have the rich type hierarchies or type composition that idiomatic C++ has. And so it's really tricky to be pragma OpenMP parallelize, simplify this, and then all of your data structures just magically get widened correctly. It's because it lives outside the C++ type system. It's extracurricular to C++, the pragma stuff. So some customers it's good, but for my particular use case with ray tracing, it just is not effective. So that's a lot of the motivation for why these SIMD wrappers I think are really useful, and why programmers looking to do more idiomatic C++, representing your problem as a type, these can be very effective for that.
It sounds, yes, very cool. And we've covered an awful lot of ground so far, so yeah. I'm just kind of thinking where to go next. There was a comment on YouTube. I know we all agreed you're not supposed to read the comments.
Yeah.
That said, basically, why didn't you just let the compiler vectorize this? And I gather from everything you've said, you're effectively, first of all, you want to fit it into specific sizes, and then second of all, you're doing things more complicated than the compiler's able to see through and vectorize.
Yeah. So OpenMP and the stuff that predates it. So OpenMP you could view as 2 things. One is the threading side. I can just put a pragma OMP parallel 4, and my for loop turns into scheduling these loop iterations on different threads. That's really useful. So the piece I'm objecting to is the other half, which is they have ways that you can say Pragma, OpenMP, basically like vectorize this. And there's two things that gets tricky with. One is like I can't make C++ type decisions on if something was widened or not. So remember we had like a V float, like a varying float in like a C++ SIMD wrapper library. Well, if I just have a float that I say, A plus B minus C equals D, and those are all plain floats, that simple expression the compiler can widen. But the problem is I've expressed it in terms of scalar code. I've said this is just a single float. That's what the C++ language says. When I say float, I get this 32-bit float or whatever the implementation decided float was going to be. Why?
Right.
Is that actually guaranteed to be 32-bit?
No.
Okay. So, but anyway, yeah.
The only guarantees with C++ types or with C types are things like double must be greater than or equal to float, long double must be greater than or equal to double, basically.
Right. But the point is it's still scalar. It's still like this is a value, not a collection of values that you can iterate over or decide to work with a subset of. You've still said this is a single variable of this, a single element. And so OpenMP says I can figure out that that can be widened to a collection that then has special instructions that can work on it. But if I wanted to have a template, I couldn't, like, let's say, specialize a function call based on am I working on a scalar or am I working on a vector's worth?
Okay.
And so, like, all of the stuff that I would want to do in the type system now are off limits because now only the OpenMP vectorizer is allowed to work with that. And the second part that's really tricky is everything has to be inlineable. So if I wanted to make a function call into something that I can't inline, there are some solutions that exist in like ICC, but it's very, very non-portable what the quality of implementation is between other compilers. To be able to say like this function call can be accepting scalar and widened varying versions of this function. So maybe if I have a function like do some math and it takes float, X and float Y and returns a float. So like, I think ICC will actually figure out how to say, I can create a version that takes a varying float X, a varying float Y and return a varying float. But in general, again, that's another thing that I don't have a lot of control over. It's just how you happen to use it and it needs to be inlineable.
Right. So,
the SIMD wrapper libraries, because they work in the type system, I can now either template a function and say this will work for any width. So, for instance, in the SIMD library I wrote called TSIMD, you have to provide vectorized versions of like math. So, like trigonometric functions, think sine or cosine or tangent. It could take a single float and return a float. You'll get that in your standard library. Or you could take a varying float and return a varying float where every element had sine applied to it or cosine.
Right.
So those kinds of things are actually width independent. So in TSIMD, I implemented it as a template that always takes floats, but any width. And then it's the exact same implementation for every single one. Like I could do that because it was in the type system that I was able to write a template based on the characteristic of this SIMD register I'm trying to program with. So those are just some of the trade-offs between like if I let the compiler do too much, I then can't take control at various points. Because for instance, like let's say I have that A plus B minus C equals D, and I say, hey, OpenMP, vectorize that for me. That's great when it does, but as soon as I say like I want to use this user-defined, I want to turn that into like a vec3f. So I took the result of that and used it as like I'm going to subtract an algebraic XYZ from it, and then that would result in another one. As soon as I start doing stuff like that, OpenMP is like, oh wait, I don't know what you're doing anymore, and gets paranoid and won't vectorize it.
Okay.
So compiler paranoia is one of the biggest barriers to compiler auto-vectorization.
Well, let's be clear. You mean our compilers wanting to generate correct code for us all the time?
Yeah, the paranoia is justified, because I, as the programmer, need to say exactly what's okay.
Right.
And so when I do it in the type system, the compiler can reason about what that should be. When I just give ambiguous, this is like one of my big objections to using raw pointers is like, I have no idea what you mean, so I'm going to be paranoid and assume that it's the worst case that it could be.
Right.
It could be an array, it could be an optional thing, is null valid. Like, there's all these things that you're not expressing when you just say, like, float star. And the same thing is true with, can I widen something or not? And when I have a user-defined structure, like, is the user depending on the layout of that structure or memory being the same? Like, there's just all these things that become justifiably paranoid by the compiler, that if you just rely on the compiler to do it and the compiler says no, then that's just what you got.
Right. So with your SIMD, with all of these SIMD wrappers that you're talking about, do they have to make runtime choices as to which intrinsic to execute?
So that is left up to, I think every single library does the same thing, which is you as the programmer say, I will compile my translation units maybe in multiple versions, and then you decide some high level point. Like the way we solve this in Osprey is we have multiple dynamic shared libraries, and we just at runtime load the one that has everything for a particular ISA. So the Osprey API is such high level that we can load the AVX 512 version of Osprey or the AVX2 version, and then we just assume everything is uniform.
Okay.
There are other solutions, like I know the Intel compiler can create like fat binaries that it does more granular function selection, but the actual wrappers themselves only make compile time decisions on what the implementation is going to be.
Okay, cool.
So you talked about a couple different SIMD wrapper libraries in your talk, including the one you worked on. I think you said that one of them is currently being standardized. Is that being aimed at C++20 or some future version?
Yeah, I believe it's aimed at 20, and it was voted in. That's the VC library. That's up on GitHub. For various then of course, then the next question is, well, why'd you write your own? And it's of course because there's objections not to like the high level, I'm going to do the entire thing differently. It's more of there's these like couple of small design decisions that we needed to do differently, and for various reasons, then I did it differently. So VC and like TSIMD, the one I wrote, are kind of the same as you would use it, but like supporting AVX 512 in the very specific ways we needed it for ray tracing. And we're talking like super in the weeds kind of design decisions, not things users should be really concerned about. But yeah, so VC is the one that I point people to because that's the one that's being standardized and lets you standard stuff as much as possible. So
one question I have regarding that is you talked about how in TSIMD you implemented your own vectorized versions of like the math functions, sine and cosine. Are there other parts of the standard library or C++ in general that are going to kind of take this vectorization SIMD wrapper into account? Like, are we going to get like vectorized versions of the standard algorithms or anything like that?
So that is a part of the parallel STL, which, that's actually so there's OpenMP, there's Intrinsics, auto vectorization, and then there's the one we didn't mention, which is parallel STL, where you say, like, I want to do std sort, but I want to do it in parallel. And there's the way that works is there's execution policies where you say, I want to do this std par, which would be parallel. Then there was like par unseek, which was technically not vectorize this, but maybe implement this in a way that could be vectorized. And I believe in 20, people out in the C++ world will correct me if I'm wrong, but there's additional execution policies being worked out by SG1, which is the study group on concurrency and parallelism, where there's like a std vec execution policy. And what that is like when you provide the little lambda to your std standard algorithm, it really says what's the license the compiler can take to vectorize that. So it's in the similar vein to like the pragma based stuff, but it's at least in core C++, and it's not something else. So these actually should compose together. So for instance, I could have, and for Jason, for your sake, I'll call it vfloat8, not float8. If I have a vfloat8, I can actually have a std vector of vfloat8s in my container, and I could write my Lambda function that will take a vfloat8 instead. So like it composes with standard algorithms already, and really I think the parallel STL solution to vectorization should be more viewed as I have some simple math I'm going to do that is all inlineable in this one, lambda that I'm going to put into a std algorithm. It's useful for more of those use cases. I would think that the real deep, very rich environment that we do with ray tracing, maybe that wouldn't be the best. But the cool thing is both of these things are aimed at the standard. Like the SIMD wrappers are in the standard. The parallel STL vectorization execution policies are also there. So it's choose the tool that better fits your problem, which I think is fantastic.
Yeah, that's cool.
Yeah. Is there anything we haven't gone over yet that you really wanted to talk about today?
Yeah, I'll just say that concurrency and parallelism and high performance computing, all that stuff is hard. So I'm really glad that there's tools out there to make some of this stuff easier. I love Sean Parent brought this up in some of his talks in like C++ seasoning. Like if you have a problem that needs to be multi-threaded, go find a tasking system. Don't implement one yourself until you are the expert in the room that knows the problem the best, that a new tasking system implementation will be better than existing ones. But I just like same thing with SIMD libraries, tasking systems, with a lot of this stuff. It's always good to find a library that solves that problem first, figure out a reason you should object to it, and then implement your own. This is all outside of like people that implement them for academic purposes. Like if you want to learn how to do this, go for it. But I mean for more production code, that is. There are tools out there that make these big, complicated problems like easier to reason about. So for listeners out there that want to get into this stuff, if you go look at those libraries, it doesn't have to be as bad as you think. And so hopefully blog posts and books and stuff out there, maybe videos will lower the bar to entry on getting involved in this stuff, because lighting up CPUs and GPUs and stuff to go bang out real fast computation is a lot of fun. So I'd encourage people to, go write a ray tracer or something like that. It's a good time. And I'll add to that, if you want to get into ray tracing specifically, check out Osprey, check out Embry. These are cool open source libraries on GitHub. But if you really want to like implement it yourself, there's a great book out there called Ray Tracing in a Weekend, put out by Pete Shirley out of NVIDIA. And he just lays out you implement your little algebraic vec3f all the way up to you then render this with ray tracing, this scene of like spheres and have cool materials that are reflective and stuff. And it's just like, it's literally in the title, Ray Tracing in a Weekend. So if you really want to get into that domain, it's an ebook up on Amazon, Kindle, and all that. So encourage listeners to go enjoy the world of ray tracing, even if it's not your day job.
Awesome. Okay, and where can listeners find you online, Jeff?
Yeah, I'm on Twitter. I'm on GitHub at Jeff Amstutz for both of those. And then I have a blog, jeffamstutz.io, that I have been terrible with updating, but I really want to get back to it. It's been a busy year, but writing's still fun, so I'm going to find some time to start doing that again.
Cool.
Awesome. Thanks again today, Jeff.
Thanks for having me.
Yeah, thanks for coming on.
Thanks so much for listening in as we chat about C++. We'd love to hear what you think of the podcast. Please let us know if we're discussing the stuff you're interested in, or if you have a suggestion for a topic, we'd love to hear about that too. You can email all your thoughts to feedback@cppcast.com. We'd also appreciate if you can like CppCast on Facebook and follow CppCast on Twitter. You can also follow me at Rob W. Irving and Jason at Lefticus on Twitter. We'd also like to thank all our patrons who help support the show through Patreon. If you'd like to support us on Patreon, you can do so at patreon.com/cppcast. And of course, you can find all that info and the show notes on the podcast website at cppcast.com. Theme music for this episode was provided by podcastthemes.com. At CppCast.com. Theme music for this episode was provided by podcastthemes.com.